Hello everyone. So in the previous session we have discussed the important theorem called Fetters lemma. So in this session let me discuss one more important theorem, monotone convergence theorem. So statement also you have to remember, this is important theorem. Along with the statement you have to write. So statement is, if fn is an increasing sequence of non-negative measurable function, and if let limit n tending to infinity fn is equal to f, then we have to prove Lebesgue integral over e of a function f is equal to limit n tending to infinity integral over e of fn. So statement you have to write without missing any of the term. So each and every term is important. So in order to prove this theorem, why? Because again you will get the same theorem, but there the statement, same form of statement, there the statement will be differ just by the wordings. So I'll let you know later. As of now, just let me explain monotone convergence theorem. So this is what the statement of the theorem is. Now we can prove this theorem by making use of the Fetters lemma that we have already discussed in previous session. So proof, I'm going to use the Fetters lemma. So that is by Fetters lemma. What is the statement of Fetters lemma says? So you have to write all those statement here. Whatever the statement of Fetters lemma is there, you just write it again. So I'm just writing the mathematical form, that is limit infimum of n tending to infinity integral over e of fn. So this is the statement of Fetters lemma. Clear? And one more important thing is that in the statement it is clearly mentioned that fn is increasing sequence. So wherever monotone convergence theorem is there, it will be applicable only for increasing sequence. So it cannot be applicable for decreasing sequence. Anyhow, I'll give you counter example for this. So let me explain first. So since it is an increasing sequence, so fn is increasing sequence. So as I already said, as per the definition of increasing sequence, if fn is increasing, I can write fn should be less than or equal to limit n tending to infinity fn, right? And moreover, limit n tending to fn is none other than f. It is given in the statement itself. So from this statement, what we can conclude is that fn will be less than or equal to f. Why? Because this value is given as f in the given statement. So this will be applicable for fn is increasing sequence. So if any sequence fn is increasing sequence, I can write these statements wherever is necessary. Fine. So fn less than or equal to f. Let me take elementary integral over both sides. So integral over e or Lebesgue integral over e over the function fn will be less than or equal to integral over e over the function f. This will be holds good for all n. Now what I'm going to take is, since I have integrated it over the variable n, now I'm going to take supremum over all the values of k greater than n. For LHS, I'm going to take supremum. Fine. So n I have written here, k greater than or equal to n. I have replaced n with k, which will be again less than or equal to f. Why? Because as this is less than f, when you're going to supremum of all this value, maximum, if the function is less than this value, if you're going to take maximum value of this function, obviously that will be less than the given function. That is the meaning. Now let me take infimum again for the LHS value. So infimum of supremum k greater than or equal to n integral over e fk will be less than or equal to integral over e f. Now this is the definition of limit supremum, right? As I already given the definitions of limit supremum and limit infimum. So whenever you have infimum of supremum, it is definition for limit supremum. Suppose if you have supremum of infimum, it will be limit infimum. Since you have infimum of supremum, so it is limit supremum as n tending to infinity integral over e fn. I can write this is the definition of limit supremum of fn, fine, which is less than or equal to integral over e f. And moreover, we know that limit, whenever you are going to take limit infimum, but limit infimum is always less than or equal to limit supremum, right? So limit supremum is highest value compared to limit infimum. Therefore, I can write this statement as integral over e f will be less than or equal to limit supremum over n tending to infinity integral over e fn, which is again less than or equal to limit infimum over n tending to infinity of a function fn, which is less than or equal to integral over e into function f. In the sense, this function f will be greater than limit supremum and will be less than limit infimum. what I have done is I have written this statement here. See here, whatever I have here, limit n tending to infinity integral over EFN is less than or equal to this value. Fine. Moreover, limit supremum value is greater than or equal to limit infimum. So this value is greater than or equal to limit infimum I have written here. So again this will be greater than or equal to f. Why? Because as limit supremum is less than f, limit infimum will be greater than or equal to the given function f. Hope so it is clear now. Fine. Now from the definition of limit, what we say, limit is none other than, that is limit supremum is equal to limit infimum. When a function is said to be tends to a limit, when a limit supremum value is equal to limit infimum value. Therefore I can write integral over E f as limit n tending to infinity integral over E of Fn. Why? Because as limit infimum and limit supremum value both are equivalent, that is it lies between the function integral over E f, so I can write both are equivalent. That is what the meaning of limit is. When both are equal, that is when limit supremum is equal to limit infimum, since they are ranging between integral over E of f, so I can write those two limits are equal. So this is what we require to prove is. So this is the monotone convergence theorem, and it is important. So one more thing is that it will be applicable for only increasing sequence. Now in the exam they'll ask you to give a counter example where the monotonic sequence is, if a sequence is in monotonically decreasing, whether this convergence theorem applies or not. So definitely it is not. Why? Because monotone convergence theorem does not hold good for decreasing sequence. So I'll give you counter example for that. Here is an example, so you have to remember this example as well. So whenever a function is defined from a set of real numbers to real number in such a way that the functions take the value 0 when the value of x is less than n, that is when it is countable. So it takes value 1 when it is greater than equal to n, in the sense up to infinity it takes the value 1. So moreover Fn is decreasing sequence. So this is the example, and let me tell you why it is not applicable. So what actually the monotone convergence theorem says, that the value of limit n tending to infinity integral over E of Fn should be equal to integral over E of f. So let me take limit n tending to infinity integral over E of Fn of a function x. Now clearly it will be equal to 0. Why? Because if it is countable for as per the function defined, the value of a function Fn of x will be equal to 0 as x is less than n. So let me take this as function f of x. Fine. Now integral over real number r. Why? Because we have defined a function over a real number r. The value of this function is 0. See here, whenever I have taken as per the monotone convergence theorem as limit n tending to infinity integral over E Fn value I have to find out. So that value will be 0 when x less than n, right? So how can I write this as integral over a function E r? Why? Because here the function is defined from set E to r. Now this value can be written as integral over E of r. Why? Because this function is defined over r. Clear? So this value is 0. Now whenever you are going to split the function Fn, I can write this as, see here, minus infinity, r is none other than, it will be ranging from minus infinity to plus infinity. Fine. So if I am going to consider this integral, I can write this as minus infinity to n Fn plus n to infinity. Again minus infinity plus infinity get cancelled. N get cancelled. This ranging from minus infinity to plus infinity, that is none other than a real number. So I can write this function as this. Fine. Now the value of this function, look at the value minus infinity to n, in the sense it is less than n. That is for lower values of n, the value of the function as we defined is 0. When n to infinity, in the sense greater than n values, n to infinity is highest values. As we reach the values of n to infinity, what is the value? It is 1. Right? So integral over n to infinity 1 into dx. Now as I already told you, integral is none other than, it represents measure of a curve or measure of a function. So I can write this as measure of closed interval n, open interval infinity. Why? Because we are starting with n including n and we end with infinity. Fine. Now as I already told you, length of any interval, length of interval is none other than b minus a. Right? So similarly here a measure is none other than length. So when you get a length, you will get infinity minus n. Again it is infinity. So this value goes to infinity. So integral over r of Fn is equal to infinity. Meaning is, see here, LHS is integral over with respect to r Fn I have. So I can write this as limit n tending to infinity of integral over r Fn is equal to infinity, but it is not true, right? Why? Because that should be equal to integral over e of a function f, but we are arriving it as infinity. Therefore we can say a monotone convergence theorem is not holds good for decreasing sequence. So I have assumed a decreasing sequence here, so it is not holds good for a decreasing sequence. So remember, monotone convergence theorem will be applicable for increasing sequence. So each and every term matters. So you have to memorize the statement as well along with the proof. Hope so it is clear. And the next concept is we say integrable. When do we say a function is integrable? Integrable is also called as summable. Fine. A non-negative, we are talking integrability with reference to a non-negative measurable function. Remember, a function f, this is definition actually, a function f is said to be integrable or summable if integral of e, that is Lebesgue integral of a function f with respect to e, should be less than infinity. That is, whenever you integrate a function, the value should be less than infinity. The value should be finite. Then only we can say a function f is integrable. Now let me study one theorem related to this concept. So here is a theorem. If f and g are non-negative measurable function such that f is less than g and g is integrable over e, then f is also integrable over e. Since it is given that g is integrable over e, we have to prove f is also integrable. Now see, proof is quite simple. Given that f is less than g, right? So I can write g minus f will be positive number, right? If something like I have given n number of times, that suppose I can write 6 is less than 7, obviously 7 minus 6 will be positive value. So similarly I can write like this. Now let us consider integrable. Since g is integrable, I can write g as, I'll just add and subtract f. So I can write this as plus f. I'll group here itself. So I can write this as integral over e g minus f plus integral over e of f. I can split this as per the non-negative measurable function properties. I have proved this in a previous session. Now, given that g is integrable, right? As per the definition just now I have told you, when do we say a function is integrable? When here it is, a function f is integrable only when integral over e f is less than infinity. Similarly here g is integrable, meaning is integral over e g should be less than infinity, right? Also, what is the, if this is less than infinity, I can write that g minus f is also less than infinity, right? So g is less than infinity in the sense, if you subtract some positive quantity, positive value of f, that will be less than infinity, right? So less than g, obviously, right? So g is the highest number. Let me give you one counter example. Suppose if g is equal to 10, I'll just give you numerical values, and let me take f as some 5. So if g minus f will be 5 only, 10 minus 5 is 5. So obviously it is less than 10, right? That is, it is less than g. So that is why I have written this statement. Now let me take integration on both sides. So I can write this as integral over e of g. Now since it is given g is integrable, that is, this value should be less than infinity. So this value is less than infinity. So I can write integral over e g minus f will be less than infinity. So if this difference is less than infinity, I can say that integral over e f, see, g is also integrable. The difference is also, whenever you are going to take a difference, again it will be less than infinity. Meaning is integral over e with respect to function f is also less than infinity. So this is the definition of integrability. Therefore I can write f is integrable over e. That's all. Only thing is, when do we say function is integrable? Only when integral of the function with respect to e should be less than infinity. Clear? Here is the next theorem, and it is also one of the important theorem. It is asked in the year 2016. Fine. So here what is the statement says? If f is a non-negative function which is integrable over a set e, then given epsilon greater than 0, there is a delta greater than 0 such that for every set a which is subset of e with measure of a less than delta, we have to prove that integral over a of function f is less than epsilon. So we have to prove this. Now in order to prove this, we have to consider two cases. What happen if f is bounded function? What happen when f is not bounded function? So we have to prove this statement for both the cases. Clear? So before that, I'll just want to revise the basics, whatever I have learned so far. So I'm sorry, whatever I have taught you so far. So whenever you have a, let me take this as a, whenever you have a function something like this, I can write this as n into measure of a. As per the property, you're going to replace n with this integral with the measure of a. Whatever the set you have, suppose if I have b here, so let me take m here. So you can write this as m into measure of b. This is the properties that you already learned, right? Now coming to the proof. So case 1, I have to, as I already told you, I have to prove for both the cases. So first case is when a function f is bounded. Bounded in the sense the function value will be ranging between some particular value. Fine. So if f is bounded function within E. So as I already told you, whenever a function is bounded, I can write that magnitude of f of x should be in between m. That is, I can write it is less than or equal to m. So this is the definition of boundedness. Then for all x belongs to E, there will be a epsilon greater than 0, and delta will be epsilon by m, again which is greater than 0, right? This is from the definition of boundedness of a function. A function f is said to be bounded if there exists m such that magnitude of f of x should be less than m, and for every, this will be holds good for all x in E, and then for every epsilon greater than 0, the delta we can choose as a small quantity such that epsilon by m is a bounded value of a function. Moreover, it is positive. Now given that a set A is subset of E, right, then measure of A is also less than delta. Why? Because it is given in the statement itself. Anyhow, it is obvious. Now let us consider integral over A f of x into dx. Fine. LHS value I am going to consider, and I am proving that RHS is true. Fine. So I can write this as less than or equal to m times integral over A into dx. Why? Because f of x is, when you're going to take magnitude, it is less than, right? If you want, I can write one more step here. See here, integral over A f of x into dx. Clear? So when you're going to split this magnitude inside for each and every term, you have to replace equals with less than or equal to. Fine. So I can write this as m into, this is none other than, as I already told you, I can write this as measure of A. Right? Why? Because I have a set A, dx is none other than integration. So integration gives the area under the curve. So moreover, it represents measure of a function, a measure of a particular set. So I have written measure of A it is. Now m as it is, measure of A is none other than delta. Right? It is less than delta. Measure of A is less than delta, so equal can be replaced by delta. Now it is less than, m into delta is chosen as epsilon by m. So m get cancelled. What you left with is capital M. So what I have obtained, integral over A f of x into dx value is, it is get cancelled, you will get epsilon. So integral over A f of x into dx is epsilon. Now whenever you have to change this value, that is I can write with reference to, we are integrating the function with reference to x only. So I can write this as integral over f A is less than epsilon. So this is what we require to prove is. So the given condition is true whenever a function is bounded. So let me prove the second case. That is what happens to the function when f is not bounded. When f is not bounded. So as we already proved one theorem that whenever a function f is not bounded, then the sequence, whatever the sequence we define, that will be definitely decreasing sequence. Increasing sequence. I'm repeating once again, whenever a function f is bounded, sequence will be increasing sequence. Not bounded in the sense sequence is increasing. When a function is bounded, sequence is decreasing. Fine. So remember these key points. Now f is not bounded. So let us consider a sequence fn defined by fn of x is equal to, I'll define one step function such that for all the values of f of x less than n, it takes the value f of x, and if f of x is greater than n, it takes the value n. So I have defined one sequence, and moreover clearly this fn should be less than n. Remember, this fn should be less than n. So I have defined one sequence in such a way that if this value will be less than n as greater values of n. Fine. Now we can note that fn is increasing sequence of non-negative measurable function. Why? Because we are talking about non-negative measurable function. So anyhow we are talking about not bounded function, that is non-bounded function. Whenever it is not bounded, so sequence is definitely increasing sequence. I'll just write one statement. Increasing sequence of which kind of function? Non-negative measurable function, such that all the sequence will be converging to say a particular value f. Fine. Now, if this was the case, as we already studied just now, the monotone convergence theorem, what it says, for every increasing sequence of non-negative function, that is what the definition, that is what we have in the statement, right? So, monotone convergence theorem will be applicable for infinitely increasing sequence, that is increasing sequence of non-negative function, right? So, we can apply monotone convergence theorem now. So, let me write here. So, by monotone convergence theorem, by monotone convergence theorem, what can I write? I'll just write the statement here. Integral over E of f will be equal to limit n tending to infinity integral over E of fn. This is from the definition of monotone convergence theorem. Fine. Now, if this was the case, I can write that for any value epsilon greater than 0 and for a positive n, I can write that integral over E fn will be greater than or equal to integral over E of f minus epsilon by 2. Why? Because fn is the larger number. So f is contained in fn. Right? F is contained in fn. If you subtract, moreover, f is always less than fn, or I can say fn is greater than f. If you subtract one small quantity epsilon or epsilon by 2 from f, obviously it will be lesser value. That is f is less, or I can say fn is greater than f. So that is what I have written. Fn is greater than f. This is obvious statement. So let me write, if this was the case, I can write integral over E f minus fn. I can write this as, I'll just split the statement. Consider this. I can write this as integral over f of f minus integral over E of fn. Now what I have told you, that instead I can say, I'll just simplify this. If you simplify this statement, I can write this. Is it clear? I'll just show you here. See here, what I have done is, I have just rewrite the statement in such a way that whenever you are going to take the difference of these two values, or else let me keep as it is, one and the same. So I'll just manipulate this statement. See here, I'll just keep this term as it is. So greater than symbol as it is. I'll just move epsilon by 2 to other side so that you will get plus epsilon by 2. I'll move this. So you will get integral over E fn. Fine. So I can write integral over E f minus fn value will be less than epsilon, or epsilon, you just rewrite this statement, f minus epsilon, fn is less than epsilon. Hope so it is clear. What I have done is, I have shifted epsilon by 2 to left hand side and this term to RHS side. So when you are going to take difference and reverse the inequality, you will get f minus fn is less than epsilon by 2. So I can write this as less than epsilon by 2. Clear? So what I have done is integral over E f minus fn is less than epsilon by 2. So let me keep as it is. Now let me consider integral over E of f. I can write this statement as integral over E of f minus fn plus integral over E of fn. So I have added function fn and plus fn, subtracted fn with reference to set A. So if you split this integral, so I'll just show you here, integral over AF minus integral over AF fn plus integral over AF fn. Again these two terms get cancelled, you will get back the same. So I can write this statement by adding fn and subtracting fn. Right? Now let me choose a delta in such a way that delta is epsilon by 2n and measure of A is always less than delta as it is given in the statement of the theorem. So integral over A, f will be, now what I'm going to do is, I'll just replace this value as I already told you at the beginning of this session, beginning of this proof. So whenever you have integral over A fn, I can write this as n into measure of A. Similarly, I can write this term as n into measure of A. Right? Capital N you have, so that is why I have written capital N into measure of A. Plus, I'll just write this statement as it is, integral over A f minus fn. Now, f minus fn integral over E is less than epsilon by 2. Since it is E, as it is given, A is subset of E. So, it will be applicable for A as well. So, I can write this value is less than epsilon by 2 plus n into measure of A is less than delta. So, I'll just write one more step. What is the value of delta we have chosen? It is epsilon by 2n. Right? Integral over A f. So integral over A f is less than epsilon by 2 plus epsilon by 2. Therefore integral over A f is less than epsilon. So this statement is true whenever a function is bounded. So in the first case what I have chosen is a function is bounded. So it is true when a function is bounded. The statement is applicable. In the second case I have chosen that function is not bounded. So the statement is true whenever a function is not bounded. Hope so it is clear. And this theorem is important. It is asked in the year 2016. Please practice the same. Now I am going to use the same result to prove one more theorem. So here is a theorem. So if f is non-negative integrable function, we have to show that the function f, which is defined by this statement, is continuous in R. So let me prove this, that is solution. So let me consider the theorem that we have proved just now. So here is a theorem we have proved. So I'll just write the theorem. So by the previous theorem, or else if you want you can write this theorem. So from the theorem, if for every epsilon greater than 0 and delta greater than 0 such that A is subset of E and measure of, I am skipping the wordings, I am just writing the mathematical forms, and measure of A less than delta, we have integral over A, f is less than epsilon. So this is what we have from the theorem I have proved just now. Fine. Now this theorem will be applicable for a real number. Why? Because if this is A is subset of E when a function is defined from E to R. Let me define a function f from R to R, then the same theorem will be applicable. Difference is that A will be subset of R. Fine. And measure of A will be less than delta. It is obvious. Now let us consider one element x0 in a real number such that for all x in a real number R, I can write that x minus x0 is less than delta. That is, for a small difference, I can write f of t into dt is less than epsilon. That is x0 to x. I am applying the same theorem with reference to variable t, and I am taking the values between x0 to x. Right? So I can rewrite this term as, I am just going to split by using the properties of integral. I'll just write it as f of d into dt. I'll keep x as it is. Now what I'm going to do is, I'll be writing minus infinity here and x0 to f of t into dt. So I'll just subtract it. Fine. Again, which will be less than epsilon. In the sense, what I have done is, I have splitted this integral into two parts. So I'll do one more step so that you will understand well. So whenever you have, as per the properties of integral, whenever you have limits from x0 to x, I can split this as minus infinity x plus x to, upper limit as it is, minus infinity to plus infinity, lower limit as it is. Now minus infinity plus infinity I can remove so that you will get the same limits, right? This is what I have. Minus infinity get cancelled. I'm going to split it by using two terms, that is two limits. That should be same. So x and minus infinity and plus infinity get cancelled, you will get x0 to x only, right? Instead I can write, since first term I am going to keep as it is, now I am going to reverse this. So I can write plus will become minus. So minus infinity to x0. That is what I have written here directly. Fine. By applying the properties of integral. Clear? Now this implies, now I can write this as, this is magnitude, I'm sorry. Now I can write this function, entire function as capital F of x. Let me represent minus, this function will be f of x naught. Why? Because when you integrate after integration, you will get capital F, right? So with reference to x, this whenever x minus x naught will be less than epsilon. Just I am applying the properties and the previous theorem here. Now this is, we can note that this is the definition of continuous function is, whenever a function f is continuous, there exists epsilon greater than 0 and delta greater than 0 such that if the difference is less than epsilon, then we can say f is continuous. So as it holds good the definition of continuous function, therefore I can write capital F is continuous at the point x0. Since x0 is arbitrary, we can take that in a real number R. So I can write f is, I can write one statement, since x0 is arbitrary point, therefore f is continuous over a real number R. And that is what we require to prove is f is continuous over a real number R. So this is what the value is. Why? Because it is given in a function itself, in the theorem itself, minus infinity to x f of t into dt. So in place of x I have t only. So f of x can be replaced. Since t is arbitrary, we can write this term as f of x, one and the same. So we have proved that f is continuous over a real number R. So whatever I have done so far, I hope it is clear for you. So please practice the same. As I already told you a number of times, almost all the importance theorem will be from 4th lesson only. Please practice as much as possible. Thank you. Continue in the next session.